Chapter 3.2, Logarithmic Functions and their Graphs. Our goals are to recognize and evaluate log functions with base A, graph log functions, recognize, evaluate, and graph natural log functions, and use logarithmic functions to model and solve real-life problems. So the inverse function of an exponential is a logarithmic function with base A. So the definition of a logarithmic function with base A is that for any x greater than 0 and a greater than 0, and a can't be 1, y equals log base A of x if and only if x equals a to the y. So the function f of x equals log base A of x. So one thing that I want you to notice is that log equals the exponent. Okay, so y log equals the exponent of the base. Okay, if you see that there. And just these little pieces. So the equation y equals log base A of x if and only if x equals a to the y are equivalent. For example, 2 equals log base 3 of 9, and that's equivalent to 9 equals 3 to the square. So again, notice this 2 here, what it equals is the exponent. 5 to the third equals 125, and it's equivalent to log base 5 of 125 equals 3. Remembering, when evaluating logarithms, remember that a logarithm is an exponent. This means that log base A of x is the exponent to which a must be raised to obtain x. For example, log base 2 of 8 equals 3 because 2 raised to the third power is 8. So let's evaluate some logarithms. We're given f of x equals log base 2 of x, and x equals 32. So we're just going to write that in there. Log base 2 of this 32 equals what? So I think about 2 to what power equals 32. So that answer is 5. Okay, so one way to do it is, to be able to rewrite it and then to evaluate it at that point. So log base 3 of 1, that's 3 to what power equals 1? Well, that is 0. Let's look at the next example. Log base 4 of 2. So 4 to what power equals 2? Well, that is 1/2. Then our last one, log base 10 of 1 over 100. So it's 10 to what power equals 1 over 100. So you know that you need to make this into the denominator. So that needs to be a negative, and then it's squared. So x equals -2. So try these 4 examples, or 3 examples at the top. Pause the video, and when you come back, I'll have the answers for you. So if you tried this out, you'd have gotten x equals 0, x equals -3, and x equals +3. The log function with base 10 is called a common logarithmic function. It is denoted by log base 10 or simply log. And so that's the log that is on your calculator. So it's log of base 10. And so what you're going to do is just evaluate each of these with your calculator and see what you get. So we plug in log base 10. We plug in 10 for x. That is just log base 10 of 10, right? Or you would see it as log of 10. And so that answer is just 1. You don't really necessarily need a calculator. Now when you plug this in, log of 1/3, you would get -0.4771. Then, if you try this last one, log base 10 of -2, what you're going to get is an error. So I don't know if you remember this from last year, but remember that we cannot have negative logs. And so it's going to be an error, or we're going to say that it's a complex number. We will solve for some that have negative values, but when you plug it in the calculator, this is what you're going to get. So go ahead and try these 3 examples down here. Pause the video, plug it in your calculator, and see if you can find the answers. Okay, you tried this out. Letter A, you would have gotten 2.4393. Letter B, you would get an error, so it's negative, so it's a complex number. And letter C, you would get -0.3010. Next, we're going to use properties of logarithms. So here are some important things to note, is that log base A of 1 equals 0 because a to the 0 equals 1. Log base A of a equals 1 because a to the first power is a. Then number 3, log base a of a to the x equals x. And a raised to the log base a of x is x. So just want you to think about that this kind of canceled out. It's called the inverse properties, so that's just one way to think about it. If log base a of x equals log base a of y, then x equals y. This is our one-to-one property, similar to our exponential one-to-one property. So let's use these properties of logs to simplify each of these. So we have a log base 4 of 1. And so again, I think about 4 to what power equals 1, and so this answer is 0. And then, of course, you can remember the property as well. That works too. This is log root 7 of root 7, and so that's just going to be 1, because root 7 to what power equals root 7, and that is just 1. And then letter C, we have 6 raised to the log base 6 of 20, so that is the inverse property, and so we know that the answer is just 20. So try these 3 below, and pause the video, and when you come back, I'll have the answer for you. So if you tried this out, letter A is just 1, letter B is 3, and C is 0. So let's use a one-to-one property to solve the equation for x. So we have log base 3 of x equals log base 3 of 12. So number one, the bases have to be the same. So the letter A, for example, it's both log base 3. So in this case, the answer is just x equals 12. Letter B, we have log of 2x plus 1 equals log of 3x. And so those are equal bases. So 2x plus 1 equals 3x. Then we solve for x. And so we get 1 equals x, or x equals 1. Then the last one, they're both the same base. So x squared minus 6 equals 10. So add 6 to both sides. X squared equals 16. And so you square root, so x equals plus or minus 4. And I know that, you're not supposed to have negative logs in here. But actually in this case, because we're squaring inside, then it's not negative anyway. So, when you're solving using one-to-one property, it's okay to get this plus or minus. And then again, particularly because we're squaring it first before we take the log, it's okay. So I want you to go ahead and try this problem here, log base 5 of x squared plus 3 equals log base 5 of 12, and you're solving for x. Okay, so if you try this out, it's x squared plus 3 equals 12. Then you subtract 3 from both sides, so x squared equals 9. So therefore you square root, so x equals plus or minus 3. So hope this helps. Thanks for watching.